Welcome back everyone. In this lecture I will continue the proof of complete reducibility for finite dimensional representations of SL2C. So, we actually stopped with some calculation in the last class. So, I will continue that calculation now and then I will complete the proof. Okay. So, we define this Casimir element of SL2C which is actually defined for any representation of SL2C. So, let us recall what it is. So, you take V to be finite dimensional representation of SL2C, say phi is that given map from SL2C to this GL of V. Okay. So, then the Casimir element which is element of endomorphism of V given by C equal to phi x phi y plus phi y phi x plus phi of h square by 2. Okay. So, we claim that this is indeed commutes with the action of GL action of SL2 of C. Okay. So, as before we just ignore this phi and then do the calculation. So, that will be easier for us. So, we just write C as x y plus y x plus h square by 2. Now, using this relation bracket x y is nothing but h. So, that means x y minus y x is h. We can rewrite this C as h plus h square by 2 plus 2 y x. Okay. So, if you are not comfortable with this, you can put phi everywhere, not a problem, but anyway this is what happening in endomorphism of V. So, now what is our claim? So, we claim that C phi x is 0, similarly C phi y 0 and C phi of h is 0. As I said in the last class, C phi x 0 and C phi y 0 will imply C phi of h is 0, because phi of h is nothing but bracket phi x phi y. So, I will only verify this, then other thing you can verify similarly. So, now let us compute what is this C phi x. Okay. So, as I said before, we can just ignore phi and then we can just compute C x, not a problem. So, this is just exactly equal to h x plus h square x plus 2 y x x. Okay. But look at h square x. So, this is actually given by just you take h x plus h x h. Okay. If you just work it out, you can see that h into h x minus x h. So, that will be the first term plus h x minus x h times h, that will be the second term. So, if you add up, you get h square x. So, then minus h x h plus h x h minus x h square. So, that is going to give you h square x minus x h square. So, now using this you can actually rewrite the identity. Again let's look at what is this second term means. The bracket y x x is nothing but y x square minus x into y x. But if you closely pay attention, so this is exactly equal to y x minus x y times x. Okay. But bracket x y is nothing but h. So, this implies bracket y x will be minus h. Okay. You can replace here by minus h. So, this is bracket y x x. So, this is minus h x. So, if you put together in the original equation, you get C x equal to, so this h x. So, this is h x minus x y, and then you get this h x and so on. Okay, maybe let us not rewrite, let us keep it as it is. So, this is going to be bracket hx. Bracket hx is going to be 2x and then 1 by 2 bracket h square x, which is just this 1 by 2 h bracket hx, which is 2x, plus the bracket hx, which is 2x again h. Then minus you have twice hx. Okay. So, now you just cancel everything and then see what you get. You get 2x, this 2 gets cancelled. So, you get hx minus hy minus 2 hx. Okay. So, but this is if you rewrite here, you can see that two x. So, this is going to be giving you 1 hx, sorry, this is plus from here. So, you write hx minus, sorry, plus twice x h. Okay. So, that will be minus 2 hx. So, then you get exactly 4x minus 4x. So, that is 0. Okay. Again we are repeatedly using hx is equal to 2x and then xh is minus 2x. Okay. So, similarly one can prove that C phi y is 0 and that would imply C phi h is 0. Okay. So, that means this C commutes with the action of G, this action of sl2C. So, now as we observed before, if you assume complete reducibility, then this action of H on this entire finite dimensional representation should be diagonizable. Okay. But that is actually indeed very difficult thing to prove at this stage, but we will construct a subspace on which this H will act. On that space it will be easier to prove that H is diagonizable. Okay. Then we will use that information to prove this complete reducibility. But before that let us do one small exercise, so which is actually very important at this point. So, if you have two operators acting on a vector space, let us say V is a vector space, again finite dimensional vector space over C if you want. Okay. So, if you have two operators on this V acting on V, let us call it E and H. So, these are all two operators acting on this V such that the bracket of E H, okay. So, that is given by some scalar times E. So, where we assume that this scalar is non-zero. So, if this happens, so then we can actually prove that this E must be nilpotent. Okay. So, this is very interesting exercise that one can do. Okay. Maybe I will outline the proof. You can also think about various proofs of this fact. Okay. The very first deduction that one can does, because C is non-zero, you can scale H and then assume that this C is 1. Okay. So, that is the first deduction. So, step 1, replace H by 1 by C H. So, then the equation reads as follows. So, E H will become equal to just E. Okay. So, now if you look at this span of this E H, okay. So, this is inside endomorphism of V, or I am looking it as subalgebra. Okay. So, I want to look at inside GL of V. Okay. So, then it is clear that this thing is actually a two dimensional non-abelian Lie algebra. Okay. So, in particularly it is solvable. So, G is solvable. Okay, because if you take the bracket between E H, you get E. So, if you take bracket between H H and E, that those things will be 0. So, it is obviously defining 2 dimensional non-abelian Lie algebra. And now we can use Lee's theorem because G is solvable. So, there will be a, so you look at the action of G on capital V. So, there will be a basis for capital V. With respect to that basis, this E and H both will be upper triangular. So, now look at E. E is actually commutator of 2 operators. So, that means E will be inside the derived algebra of G. So, in particularly with respect to the same basis, this E will be actually strictly upper triangular. So, that proves you have a basis of V with respect to that basis, this E is actually strictly upper triangular. So, that means E must be nilpotent. So, this is one proof that one can use representation theory and then prove it, but I will also encourage you to actually find some other proof. For example, like once you write E H equal to, once you write E H equal to E, then it is not hard to see what will be E square H. So, from our earlier formula, E square H is nothing but E times E H plus E H times E. So, now use this formula bracket E H is E, then we get E times E square plus again E square. So, that will give you 2 E square. So, basically E H is E and 2 E square is just again bracket of E square H. So, what this implies? This implies trace of E is 0 and as well as trace of E square is 0. So, now if you have an operator acting on a vector space V over complex numbers. Okay. So, this is again exercise. If T is an operator from V to V, V is finite dimensional vector space over C. Suppose trace of T power k is 0 for all k. Okay. So, one can assume to be k varying from 0 to sorry not 0. So, k is varying from 1 to dimension of V, but anyway if it is true for all n. So, this implies that T is nilpotent. Okay. This is also one characterization of T being nilpotent, because if T is nilpotent then any power of T will be nilpotent, and for any nilpotent operator you know the trace must be 0. So, this is one characterization of nilpotent. Now, what this computation says, trace of E is 0, trace of E square is also 0. Similarly, it is not hard to see that if you take E cube and then compute H, the bracket of that, then it will be again E square H plus E square H E. So, then that will give you that this is E cube by 2, sorry 2 E cube plus. So, E square H is 2 E square. So, this is 2 E cube plus 2 E cube. So, you get 4 E cube. For this you can simply see that E into E square H minus H E square plus E square H minus H E square into E, you get E cube H. So, this E H E square, oh then okay, maybe I need one term. So, here yeah, so what we are getting, so this is E cube H minus E H E square plus E square H E and then minus H E cube we are getting. Okay, maybe I need to again add and subtract some more terms. Okay. but you can actually again prove that it will be a some multiple of E cube. Okay. Maybe I will leave it to you to check. So let us see. So what we need to add and subtract. So you can actually see that you need only to understand what is happening with this E H. Okay, you can take E H E outside. So then you can see that. So this is you are going to get E. So this E cube H and minus H E cube will give you this bracket E cube H. Okay. Yeah, but yeah, if what will happen if you replace this? So let's do this computation here. Okay, so this is I am trying to compute what is happening here. Okay, so you are getting U cube H and then minus E. So you can actually replace E square H minus the bracket H E square. Okay, and then plus again E cube H can replace bracket H E. Okay, so this is the term that you get. So you can see that this and this will get cancelled. So you get E cube H plus E times H E square. So H E square is minus 2 E square. So minus 2 E square, and then this term will be minus E square. So again H E will be minus E. So you get E cube H is equal to minus twice E cube minus E cube. Okay, so this is what you are getting here. So this is going to be equal to 4 E cube. So in particularly you can see that E cube H is nothing but some multiple of E cube. Okay, so whatever it is. So this way what I am trying to say, so if you compute any e power k h, you can see that there will be a non-zero scalar here and then e power k will be there. Okay. So this is something you can easily verify. That would imply that trace of e power k is 0 for all k. Okay. So that will imply that E is nilpotent. So this is one way to verify by doing explicit computations. Okay. So here I have used solvable Lie algebra representation 3 to prove that E is nilpotent. So we can also use invariance lemma again to prove the same thing. Okay. So why the invariance lemma? Because if you take this span E inside this G, where the span of H and E, okay. So this is going to be ideal. So this is going to be ideal inside G. So in particularly you know that if you take any eigenspace of this E, so that should be invariant under both H and E. So but E is nothing but bracket H E. Okay. So that says that the trace of this E on that eigenspace must be 0. But on the other hand, what will be the trace of E on the eigenspace? So that will be just trace of E restricted to V lambda will be just lambda times dimension of E. So, that should be 0 because E is nothing but the bracket of H E. So, that makes lambda to be 0, but lambda is any eigenvalue of E. So, now we proved that it should be 0. So, that proves that E must be nilpotent. Okay. So, there are many ways to prove the same fact, but what this fact immediately implies you. So, you recall what is happening in sl2c. So, you write Hx equal to 2x. Okay. Similarly, Hy is also equal to minus 2y. So, this is exactly of this form. Na? So, you go back to your original exercise. So, you have this He is nothing but some E C times E. So, then you are claiming that E must be nilpotent. So, that is what happening inside SL2 also. So, if SL2 acts on some finite dimensional space V. So, if SL2 acts on some V where V is finite dimensional vector space. So, then using this formula you can immediately conclude that both x and y are nilpotent on capital V, acts nilpotently. Okay. On capital Y. So, that is immediate. So, now let us use that and then conclude our result. Okay. So, we are going to make another important statement. So, like I said, we have some information about x and y. So, this is nothing to do with SL2 representation 3. Basically, this Hx being 2x implies that x should be nilpotent, and similarly for y you have nilpotent. So, now if you start with finite dimensional representation of SL2. So, as we predicted, the element H should act semi simply on this V, but that is hard to prove, as I said. So, what we do, we restrict this action of H to the what is called the kernel X. So, this is going to be mapped from kernel X to kernel X, and we can claim that this is indeed nilpotent, is diagnosable. So, first of all, why this defines a map? Okay, let us see that. So, what is the definition of kernel X? The kernel X is those vector in V such that X kills that V. Okay. So, now you take some V in this and then apply H, and then we want to claim that HV is also in kernel X. So, compute what is happening to XHV. So, XHV is nothing but HXV minus HXV, okay, because I have used it in reverse way, but XV is 0 already. Then what is HX? HX is 2x, that is also acting on V. So, that is also 0. So, that implies HV is again inside the kernel X. So, this implies when you restrict H to kernel X. So, this maps kernel X to kernel X. So, it makes sense that whether this map is diagnosable or not. So, that is again simple computation, I will leave it to you to check. So, first there are two identities. Okay. The identity 1 says if you apply x y power k v, so that will be equal to y power k x v plus k times y power k minus 1 times h minus k plus 1. So, this is true for all k greater than or equal to 0 and V in capital V, and this is true for all V in V. Okay. It is not only restricted to some kernel X or anything. So, this identity is true for any vector V in V. So, we are thinking this x and y, they are all elements of endomorphism of V. So, we are repeatedly applying that x and y. Okay. So, this is true. So, now this is just induction, I will leave it to you to check. So, now what is the second identity says? So, if you restrict to kernel X, then we have this following important identity. So, we can see that if you take x power k y power k v, okay, for v in kernel x, then what happens? So, this is going to be equal to some k factorial times h into h minus 1 times etcetera h minus k plus 1 v, and this is true for all k greater than or equal to 1. So, this is always true for only elements in kernel x. Now, we claim that this identity 2 immediately implies h must be diagnosable on this kernel x. Why? What do? You take y. So, this y acts nilpotently on this capital V. So, that means y power n for some large n. So, that is 0 for all v in V. Okay. In particularly this y power n v will be 0 for all v in kernel x also. Okay. So, then if you take this and then substitute back here for the capital N, you can see that x power n y power n v. So, that should be 0, but on the other hand you get n factorial times h into h minus 1 etcetera h minus n plus 1 v. Okay. So, that proves that h into h minus 1 etcetera h minus n plus 1, this is identically 0 on kernel x. So, that means the minimal polynomial of h restricted to kernel x, that is going to divide this polynomial, but this polynomial has all the roots distinct. Okay, because what are all the roots? Roots are 0, 1 etcetera n minus 1, these are all the roots. Okay. So, the roots of this polynomial this. So, that implies that the minimal polynomial of h restricted to kernel x, okay, this polynomial maybe polynomial in t, that is going to divide this t into t minus 1 etcetera t minus n plus 1. So, that implies that, so the roots of this minimal polynomial are all distinct, roots of this minimal polynomial are all distinct, and that implies that this h restricted to kernel x must be semi simple or diagnosable. Okay. So, this proves that this h restricted to kernel x must be diagnosable. In particularly we can get a eigen basis, okay, so that completely diagonalizes this h. Okay. So, now if we go back to the representation capital V. So, this is a finite dimensional representation of sl2c. So, then as we seen before, if we take this Casimir element, so this Casimir element is actually commutes with the action of this sl2c. In particularly I can break V into direct sum of this V theta, where theta is coming from C. So, this is this primary decomposition. With respect to theta, okay, sorry, with respect to C. So, then we saw that each, so this V theta, what is the definition of this? This is the kernel of C minus some identity power n. Okay. Let me call it n. So, we know that sorry theta, this is going to be again sl2 submodule. So, if you are interested in proving complete reducibility for finite dimensional representation of sl2c, so it is clear that we can assume this V equal to some generalized eigenspace of this C. Okay. So, what is the meaning of that? So, here is the important property of this generalized eigenspace. This Casimir element C, it has only theta as eigenvalue on this V theta. Okay. So, there is no other eigenvalue. So, we can assume that without loss of generality that theta is the only eigen value of C on this capital V, okay, by looking at the primary decomposition. So, now in this case if we decompose V into direct sum of irreducible representation, then we are done. So, for that what we do, we first understand some of the things. Okay. So, we can actually collect all possible sub representations of this capital V. If you take non-zero sub representation which has smallest dimension, then it is easy to see that sub representation must be irreducible, because it cannot contain anything proper inside, because this is that is the smallest representation. So, in particularly given any finite dimensional representation, we can always have irreducible sub representation. Okay. So, if you take for example V of m to be one particular finite dimensional irreducible sub representation of this capital V, then what will happen? So, then we can calculate how this C acts on this V m. Since this is actually sl2 sub representation, so C will map V of m to V of m, okay, because C is nothing but what? X y plus y h plus h square by 2. Each element in this expression will map V of m to V of m. So, C will map, but C has eigenvalue only theta, but C also commutes with the sl2 action. So, by Schur's lemma, C must be some scalar times identity on V of m. We also computed what is that scalar. So, we know that C restricted to V of m is nothing but m square by 2 plus m times this identity on this V of m. Okay. But theta must be only eigenvalue. So, in particularly this forces that theta must be equal to m square by 2 plus m. Okay. In case there is another irreducible representation sitting inside this V, then again from this earlier argument we see that C restricted to V n should map V n to V n, and not only that, C restricted to V n should look like again some scalar times identity. That scalar is given by n square by 2 plus n times identity. So, that forces that again theta must be equal to this n square by 2 plus n. So, if this m, let us say we have fixed, if this is another one, then what it says, this forces that this m square by 2 plus m must be equal to n square by 2 plus n. But this is actually a quadratic polynomial having two non-negative roots. So, then it must be those two roots must be same. So, that is easy to see. So, that proves if I take any other irreducible copy of irreducible sub representation of this capital V, that must be copy of V of m. There is nothing else that can sit inside capital V. So, what is the observation that we made? So, the observation that we made, so first of all there is a, so what is the assumption that we actually made? So, if C has only one eigenvalue in capital V, okay, so then any irreducible sub representation V m of capital V should satisfy m square by 2 plus m equal to theta. Okay. So, that means this implies all irreducible sub representations of capital V are the copies of V m. Okay. So, this is a very very important observation. So, now look at the action of H on the kernel x to kernel x. So, we know that this is diagonalizable. So, that is we already proved. Since this is diagonalizable, I can actually fix a eigenbasis. So, fix a eigenbasis V1 etcetera VR of this kernel X. So, that means what? X Vi kills and this H Vi acts as some scalar, okay, call it mu I Vi. But the thing is, so then this Vi becomes maximal vector, okay. So, because X is killing and H is acting as scalar. So, this naturally becomes maximal vector, but if we have a maximal vector, we just if you go back to our irreducible representation argument. So, we will be able to generate sub representation generated by Vi. So, that you can prove this is span of Vi, y Vi and so on some y power n I Vi. So, in particularly this sub representation will become irreducible. So, this becomes irreducible representation and this will become isomorphic to naturally V of n I. Okay. So, that forces this mu I is equal to n I. Okay. So, we have these sub representations generated by Vi and then we know that whatever highest weight or the maximal eigenvalue that will be n I. So, now what we are going to do? We are going to take this V of j to be that copy of V of n I. So, what is that copy? You take to be span C just V j, y V j and so on y power n j V j. So, this is going to be isomorphic to V of n j. Okay. So, all these are irreducible sub representations of capital V. So, now what is the claim? Natural claim is V will be isomorphic to or equal to summation V j, j range from 0, j range from 1 to r. Okay. So, that is the idea. So, basically what we are doing, so we are looking at the kernel X. So, this kernel X is spanned by V1 etcetera VR, okay, and these things we are choosing it to be eigenvectors for H. So, this will corresponds to n1, this will corresponds to nr as H eigen values. So, then we just generate copies of sl2 representation from this, because these are all maximal vectors. So, you take V1 and then apply y V1 etcetera y power n1 V1 and then take y V2 etcetera y power n2 V2 and so on, then y VR etcetera y power nr VR. So, each one will you give you one copy of sl2, sorry, one copy of irreducible representation. Now, from your earlier argument what you are actually getting. So, if you take this C has only one eigenvalue inside capital V, then any irreducible sub representation must be isomorphic to V of m, where this m satisfies this m square by 2 plus m equal to theta. So, that means all irreducible representation are copies of V of m. So, if you put together, then you can see that this n1 must be equal to n2 etcetera must be equal to nr. Okay. So, basically you are getting only the same copies. So, you have V1 etcetera VR and then y V1 y power this m V1 etcetera y VR etcetera y power m VR. So, this is going to be your copies of Vm inside your V theta. If you add them together, you can get it for any finite dimensional representation. So, let us see why this is true. So, that is what we are claiming. So, first thing to note, this actually exhausts entire thing. So, suppose summation V j, j ranging from 1 to r, if this is a proper subspace, then what will happen? If this is a proper subspace, then we can actually consider this submodule. Okay, this is going to be a sub representation. Okay, then this is going to be your factor module. Okay, so this is a factor module, and this is going to be non-zero module. So, this is non-zero module finite dimensional. So, it must contain some irreducible finite dimensional representation, sub representation. So, let us say V dash, this is sitting inside V modulo summation V of j, j range from 1 to r. So, this is finite dimensional irreducible sub representation of this V modulo summation V j. Okay. Now, you know that how this capital V dash should look like. Okay. So, this V dash definitely generated by some maximal vector, call that maximal vector V bar. So, V bar inside V dash. So, this is maximal vector. So, x V bar is 0 and h V bar is given by some p times V bar, where p is coming from some z plus. Okay. So, now go back to this Casimir element. So, this is a element that is actually maps V to V. Since the summation V j, that is also submodule, so it maps summation V j to again V j, summation V j. So, in particularly this C bar induces a map from V modulo summation V j to V modulo summation V j. Okay. So, now this C bar actually maps this factor module to factor module, since C actually commits with sl2 action. So, C bar also commits with sl2 action, and since V this factor module is a quotient of V and C has only one eigenvalue inside V. So, that would imply that C bar also has only one eigenvalue, has also only one eigenvalue in this V modulo summation V j. So, what is that? Namely, that should be theta, nothing else, okay, because this is just induced from C. So, now what we can do, you can take this C bar and then restrict it to that V dash. So, it has to map V dash to V dash. You can now you can see that if you compute this, what will be the action of C bar. So, this is going to be some lambda times again identity on V bar V dash, because V dash is being irreducible. So, by doing this earlier calculation, you can see that on the one hand you get theta, on the other hand you get p square by 2 plus p. But since m square by 2 plus m is same as theta, and then p square by 2 plus p is also theta, that forces p has to be equal to m. Okay. If p equal to m, then actually you get h v bar equal to m v bar and x v bar equal to 0. Okay. So, then you can write this V bar into some V plus summation some elements coming from V j. Okay. So, j from 1 to r. So, then you can see that because x is being nilpotent, x is nilpotent on capital V itself. So, then there exists some k such that x power k v will be in kernel x. Okay. Because x is nilpotent on capital V. So, that implies this x power k v is actually maximal vector with h eigenvalue m plus k. So, x into x power k v is 0 and the h eigenvalue of this x power k v. So, that should be m plus 2 k, because this V bar has h eigenvalue m. So, this V you can choose it to be coming from that mth eigenspace. Okay. So, that is why you have this m plus 2 k eigenvalue, but you already know what are all the eigenvalues of this H na. So, the eigenvalues of H on this kernel X, okay. This H is defines a map from kernel X to kernel X. We already saw that all these Vi's that we have chosen to be eigenbases, they all have eigenvalues exactly m. So, that forces this m plus 2k must be equal to m. Okay. So, this is equal to m implies k must be 0. If k is 0, then that means already the vector that you have chosen, that is already in the kernel X. Okay. But that means what? That means V is in summation V j. So, that implies V bar is 0, but by the choice of V bar we cannot have 0. So, that contradict your assumption. The assumption is the summation V j is proper inside capital V. Okay. So, that proves that capital V must be equal to summation V of j, j ranging from 1 to r. So, now we want to prove that this is also actually direct sum. So, if not, then what will happen? So, there exists some again non-zero vector which will be inside this V of j intersection all this other V of summation V of k, k not equal to j. Okay. But if you take this V of j intersection summation this V of k, k not equal to j. So, this is actually a submodule inside V j. So, V j being irreducible, and because there is a non-zero vector inside this. So, this is being non-zero submodule that forces this V of j intersection this summation V of k, k not equal to j, this has to be exactly equal to V j. But V j is what? V j is generated by small v j. So, that forces that this small v j is an element of summation V of k, k not equal to j. But where is V j sits? V j is in the mth eigenspace. Okay. So, what will be the mth eigenspace of this? Mth eigenspace of this will be spanned by this small v k, k not equal to j. So, that will be the mth eigenspace of this summation. Summation V k, k not equal to j. So, that forces that this V j is in the span of this V k, small v k, k not equal to j. Okay. But that is a contradiction, because by choice V 1, V etcetera V r, they are all actually linearly independent eigenvectors of that kernel X. Okay. So, that says that the sum that we have is actually direct sum. So, this proves that V must be exactly equal to the direct sum of V j. Okay. So, it is actually a very interesting proof. This proof actually does not use any other information from any other theory. This is more self-contained proof. So, this proof again uses some elementary facts from linear algebra, and then proves the complete reducibility for SL2. Okay. So, I would actually kind of recommend you to kind of go through this proof very well, because this proof you will not be able to find anywhere else. Okay. So, I will actually upload the notes for this proof, okay, that will help you to actually understand it better, but I recommend you to really go through this once, because then only you will understand what happens in the general case. Okay, I will stop here, and we will continue with the structure theory of semi-simple E-algebras in coming classes. Okay, thank you.